In our previous lesson, we learned to predict if a precipitation reaction would occur. And now we're going to go through and learn all the different ways that you can write a precipitation reaction taking place. There are various ways to do that. Okay? So what we had just written in our previous lesson was called a molecular equation. It's a bit of a misnomer. It really is a bad word for it because these are not made up of molecules. But since they're written in a combined state, they call them molecular equations. Ionic compounds are not made up of molecules. To refresh your memory, they are formulas. Formula units is what we use to represent them. But because they're three-dimensional shapes that go off and are very large. But when we write the cation and anion combined together in all reactants and products, that's called the molecular equation. What we're going to look at what to write next are the complete ionic and what's called the net ionic equation. Net ionic equations are the most common way of writing, maybe, I don't know if it's most common, but it's a common way of writing these precipitation reactions. We're going to also see that the ionic equations can be used for other types of reactions as we proceed on. Okay, so how do we write the complete ionic equation? What we're going to want to do is we're going to take our ionic compound that's written and break it apart into the ions that it really exists in. Because remember, these ionic compounds, if they're soluble in water, when they dissolve, are strong electrolytes. All ionic compounds are strong electrolytes. So when they go into solution, they completely break apart into ions. So we're going to represent them that way, separate from each other in solution. Okay? And then you'll do the swap, and then you will have your products. So I wish now that I had left my reaction equation up on the board, but you've got it there in your notes. Let's go through and break those ions apart to give what's called the complete ionic equation. The first thing we had up there was the potassium phosphate, right? And we had it written as K3PO4. Well, K3PO4 is going to break apart and be the cations, which there are 3 of them. We call it K+, and we would put an AQ after it, okay? So the 3 ions don't stay hooked together with a 3+ charge. Each one of those, they're monatomic ions, and there are 3 of them that are floating around in solution. And then there's one of the PO4, so we write PO4 with a 3- charge, and it's aqueous, AQ, okay? The second substance in that reaction equation was the iron 3-acetate, and we had written that with 1 iron, so we put Fe3+, AQ for aqueous. And then there are 3 of the acetate ions. Now when it dissolves, those 3 acetate ions don't stay hooked together. They're just floating around independent of each other. So we use a 3 in the front to say I have 3 of these acetates. And I think I'm going to write it this way. C2H3O2-. There are 3 of those. Those are my reactants. Okay, and that's when you write it out as the complete ionic equation, it takes up a lot of space, doesn't it? All of those AQs in there. And then if you look at the right-hand side of the equation, we had the potassium acetate, and there were 3 of them. And that would give me 3 potassiums. That would give me 3 acetates. Both of those are aqueous because the solution is soluble and it stays in solution, and those ions are floating around separate from each other. But the one thing that doesn't break apart is the solid. We keep the solid intact. So we have the FePO4, and that's a solid. And that is how you write the complete ionic equation. Every ion that was put into there is represented in this equation. If it's in solution, they aren't touching each other. They're floating around independently because they are strong electrolytes, and we know they break apart. But the thing that is insoluble, that we write the S out, it is kept intact because they are not floating around independent of each other anymore. They are packed into their crystalline structure of an ionic compound. All right. Let's do this one, and we're going to leave room for the other type of equation for that in a little bit. What is the insoluble salt form between sodium sulfide and nickel chloride? Okay. Stop and see if you can figure that one out, all right? You stop the video and you try to figure out what the insoluble salt would be. Think of the partner swap. Okay, hopefully you took the time to do that. If you followed the rules for that one, I'm going to leave myself some space up here. If you follow the rules for that one and you do a partner swap, you're going to get the nickel sulfide as the solid that would form. This would be the precipitate that would form in that reaction equation. Okay? But if we wanted to write the actual chemical equation, this is just a formula for the precipitate, which is what we figured out. Let us work together at writing the molecular formula and the ionic formula to form that precipitate. Now you might have done all this work in order to figure out your answer. So let's write Na2S, that is aqueous, and NiCl2, that's aqueous. We do the partner swap, so the nickel and the sulfur get together, and the sodium and the chloride get together. That's the formula of sodium chloride, okay? We go through in our mind the solubility rules, and we know that this, according to the solubility rules, is insoluble, so it gets an S. But this, according to the solubility rules, is soluble, so it gets an AQ. Now look at this equation. Is it balanced as you're seeing it here? Well, it's not, so we'll need to balance it, and I think that if I put a 2 right here, that's 2 sodiums and 2 chlorines to go with these 2 sodiums and these 2 chlorines, then it would be an equation that's balanced. Now, which type of equation is this? Is this the molecular equation or the ionic equation? Well, this is the molecular equation because we're keeping them intact. So you might have done all this work to answer what would be the precipitate, or you might have just thought, okay, if I swap partners, which one of those partners is insoluble? But there is the equation for that. Now to write the ionic equation, we would break this apart into its ions. See that 2? Let me do it this way. You see that 2? Does it stay where that sodium is, or is sodium a monoatomic ion and I happen to have 2 of them? Well, it is a monoatomic ion and I have 2 of them. So I have 2 Na plus, that's aqueous. I have 1 S2 minus, that's aqueous. I have the nickel, and the nickel's got a 2 plus charge, and it's aqueous. And the chlorine, it's a monoatomic ion as well. It is not a diatomic molecule here. This is a monoatomic ion in this compound. So there's 2 Cl minuses, and that's aqueous. On the right-hand side, this is a solid, so it stays intact. NiS solid. And then we have 2 of the sodiums. So I write 2 Na plus aqueous, AQ. And then we have 2 of the chloride, so it's 2 Cl minus, aqueous. So there is the molecular equation on top, and the ionic equation, which we call the complete ionic equation, on the bottom. Oops. So now what I want to teach you is something called a net ionic equation, and I thought that I had words up here to describe a net ionic equation. Let me just back up and make sure I haven't missed anything. Nope. All right, so to do a net ionic equation, bear with me. Nope, it's just not there. Okay, to do a net ionic equation, what we're going to do is we're going to get rid of what are called spectator ions, okay? So we need to remove spectator ions, and this will give us what is called a net ionic equation. When you think about your net pay, it's how much you got to take home, right? It's not the complete pay. That's what the employer put out and had to pay out. But what you got to take home is your net pay. The net ionic equation is what is really happening. So we have to remove what we call spectator ions. Well, spectator ions are ions that are in the reaction, they're floating around, and they never do anything but float around as ions. So let's look at this top equation and let's find our spectator ions. To find a spectator ion, it looks identical on both sides of the equation. So I have 3K pluses here and 3K pluses here, and they're going to be canceling because they're on opposite sides of the equation. What else? Well, the PO4 looks different here as it does here, because here it's AQ and here it's part of a solid. It doesn't look identically on both sides, so I can't get rid of it. How about the iron? Same thing, Fe3 plus here, and the PO4, I'm sorry, the Fe is inside this compound here, so I can't get rid of it. And then we have the 3-acetate ions and the 3-acetate ions. They look identical on both sides, so I can cancel this on the left-hand side of the arrow and this on the right-hand side of the arrow. And then I can write what remains. Now, I'm kind of in the habit of writing my cation first. Doesn't matter. It's not going to be wrong if you wrote them in the order that you see up here. But I generally write the cation first, then the anion, and you see that what we're left with is the PO4. I mean the FePO4. So that is called the net ionic equation. Now let's go down to here to do the net ionic equation of this one. We're going to look at the ionic equation, which is the bottom one, and we're going to go through and find anything that appears exactly the same on both sides of the equation. Well, I see 2 Na pluses here and 2 Na plus aqueous here, so those are identical. The S2 minus aqueous, but I come over here and the S is inside that precipitate, so I can't cancel that one. The nickel 2 plus aqueous versus the nickel inside a solid, I can't cancel that one. The 2 Cl minuses and the 2 Cl minuses, yes, I can cancel those. And that's going to give me the nickel 2 plus aqueous plus the S2 minus aqueous, and the product is NiS solid. So that's my net ionic equation right there. Now, you can do a shortcut from what you see written on the screen here, okay? So we see what is the insoluble salt formed between those. And we came up with this as our solution to it. Once you know what the precipitate is, you can jump straight to this. Just put the precipitate as a product and the ions that make it up as reactants, and you don't have to go through each one of these steps to get to a net ionic equation. A net ionic equation, of a precipitation reaction will always be the solid on the right and the ions that make it up on the left, and you've got yourself an equation. So, I expect you to be able to look at what's being put into solution and be able to determine the products of a precipitation reaction. I expect you to be able to write it in the form of a complete ionic equation, a molecular equation, a complete ionic equation, or a net ionic equation, and I expect you to know the definition of what a spectator ion is.